Okay, let's talk about this gas effusion problem. And what happens is when you let a gas into a room through a small hole, so it's just like spraying gas into a room, the smaller particles move faster, the larger particles move slower. Or if they're the same size, the hotter particles move faster and the colder particles move slower through the room. That is what we're talking about when we're talking about the rate of effusion. Specifically, effusion is the gas particles moving into a vacuum so that there's no other particles getting in the way. So let's compare their speeds. We have one gas that moves 1/5 as fast as helium gas when they move through the same opening. So one of them moves way faster than the other. They're implying that they're at the same temperature because they're not comparing temperatures and they're in the same room, so that makes sense. So let's look at our equation here. This is the speed of a particle in a room, really, but mostly in a vacuum. It's the root mean squared, and it's basically like kind of like the average speed. Doesn't matter the direction or any of that stuff. So it's equal to the square root of 3RT over the molar mass. So the particle moves faster if you have a higher temperature or if you have a smaller molar mass. Or if this number is large, this speed goes down. So if one of these gases is 1/5 as slow, that means it must be larger, because that means this is a big number here. The speed must go down. Then the one that moves faster, phew! So it has to be way bigger than helium. So let's figure out what it is actually, what the molar mass of this gas is. And what we're going to do is we're going to use the rates of effusion comparison equations, and it's the speed of one over the speed of the other. Speed of A over B is equal to the square root of the molar mass of B over A. And that comes from getting the speed of one of these, root mean squared of A, and then dividing it by the root mean squared of B, and then canceling everything that's the same. So in that case, the temperatures cancel, the R's cancel, the 3 cancel, and you end up with the molar mass. And then they do that little algebra magic, and they end up being flipped. Try it out at home. You'll get there. But you don't need that right now. Just know how to use the equation. So let's put in A over B. It said that this one is 5 times as slow, 1/5 as fast. That's the same thing as saying that this is 5 times as fast as this one. So I have a 5-to-1 ratio of helium to this guy here. Alternatively, you could flip it and then do 1-to-5 and flip it. This was my choice for this calculation. Square root of mm of the one on the bottom, the molar mass of X is what I'll call it, and then over the molar mass of helium, which I know. So since it's a 5-to-1 ratio, and let's solve the darn thing here. So I do square both sides to get rid of the square root, and I end up with 5 squared and then mmx over mmhe. And there it is, algebra time. This, I know the molar mass of helium, which is 4.003 grams per mole. Look, I put the wrong thing on there. I put H2 for some reason. Who knows why, but I solved it. And I wrote a little line through it so I can keep track of my errors. And I solved for the mm of X, bring this thing over, and it should be 100.075 grams per mole. Depending on the sig figs, it should be about 100.1 or 100 grams per mole. It's funny because there are really no sig figs in here. I was talking with another student, so you don't really know what limits you have. I think this is these 4 digits here is the number that limits us, so let's limit it to 4 digits. Okay, there you go.